Welcome to Math 31. This is a lesson on symmetry. So moving away from some of the other pre-calculus topics that were a little more algebraic in nature, this is focusing principally on the graphs and the characteristics of graphs. Symmetry, as you would have dabbled in a little bit in 30 Pure, but it is looked at a little bit differently here. So to begin, start with this simple quadratic, f of x equal x squared. And I'm putting in a few points along the way for these, a few ordered pairs. Now the 2 and the 4 you can see a little bit off, should really be up there, if you really care about that. And if you were to examine this graph carefully, it might occur to you that the graph is symmetric with respect to the y-axis. It's a perfect mirror image on the other side of it. And when you look at these points that we have labeled, you'll see that they reflect to the other side of the y-axis. So 2, 4 transforms into negative 2, 4. Actually, it doesn't really transform because it's on the same graph. It would just have a mirror image on the graph. So it means also that any point that you've got xy that's there is going to also have negative xy. So the same y value will produce two x values of the same amount, just a different sign. And we call this an even function. So when a graph is symmetric with respect or about the y-axis, it is even. And as I noted earlier, xy and negative xy both lie on the function itself. So that's how we describe visually an even function. Now if you were then going to consider a cubic function, f of x equal x cubed, looking like this, pretty routine looking graph, with a few points on it, you'll notice something somewhat remarkable. This graph will have ordered pairs like 2, 8 there, and then you'll also have negative 2, negative 8. Same thing happening with 1, 1, and negative 1, negative 1. And in fact, this would be true for every xy point up there. There would be negative x, negative y down there. And we would describe this graph as being symmetric with respect to the origin. Now, what we really mean when something is symmetric with respect to the origin is that the graph is reflected in both the x and the y-axis. So like if you took a look at this function, and if you reflected it first off in the y, this would be kind of rough because it's a tough one to draw, but this is what you're going to get, a graph looking like this. Sort of. Now that's reflected in the y, and then if you reflected it into the x, in the about the x-axis, then you'll see that you end up with the mirror image of it. So it ends up being the same as the original, in fact. So when something is symmetric with respect to the origin, you could also think of it as being perfectly reflective around the x-axis and the y-axis. And we call this an odd function. And everybody says, well, what do you call something that is just reflected in the x-axis, or is perfectly symmetric in the x-axis? Well, it doesn't have a name because that wouldn't be a function in that case. If a graph is a mirror image around the x-axis, it would not be a function. So we have even when they are symmetric with respect to the y-axis, and we have odd when they're symmetric with respect to the origin. And as I noted earlier, xy and negative x, negative y both lie on the function. Y equal 1 over x is a very common function to be used to describe or to get a look at an odd function, because this is odd. So we would say this is an odd function. It is, in fact, not odd in the way people use the word typically, but it's odd in that it's symmetric with respect to the origin. So you can kind of see this. If you had a point there, for example, which is about, let's pick this one instead. It's a little easier to see, 1, 1. Then negative 1, negative 1 will also lie on this function. So that's how these ones work. And the same would be true for any other point that you had. That's a 1, not a 2 down there. Now you're probably wondering, how do I recognize this with the equations? And really that's what it is all about. After a while you develop an eye for seeing the graphs, but the equations are a little different. And here's basically how that works. As you may have concluded when you were looking at the three previous graphs, if we have f at negative x equal to f at x, then we say that the function is even. So that's why we would have the quadratic being this. It means that if you replace x with negative x, you end up with the same function. And then, if you replace x with negative x, and you get a negative version of the function, negative f at x, then we say that it is an odd function, which means it's symmetric about the origin. Now that may not be perfectly clear, but the method would go like this. You replace x with negative x into the function, and then you observe the simplified form. And if you get this, if after the replacement it's still equal to the original, then we say it's even. If you get a negative version of the original, that is just a factor of -1 multiplied by it, then we say it's odd. And if it's not one of those two things, then it's neither even nor odd. So let's do a few, and I think that you'll probably get this one down. So if f of x is equal to x, absolute value of x minus 3, well, all we need to do is replace that x with negative x, and then see where it takes us. So x gets replaced with negative x. So f at negative x is equal to the absolute value of negative x minus 3. Thing of it is, the absolute value of negative x, well, you take the absolute value of a negative, and it becomes positive. So it's the negative x is the same as the absolute value of positive x. So therefore, we could make this statement. F at negative x is equal to f at x. And if you go back to the previous display, you'll see that that means that it is even. So therefore, even. That's all you have to do. See where it takes you when that x gets replaced with negative x. And there's the graph. So by inspection, you can see that it is a mirror image around the y-axis. It's perfectly, if you folded the paper over right on the y-axis, the curves of the lines would line up perfectly. Let's try a few more. F at x is equal to 2x to the 4 minus 2. Now, you'll develop some pretty clear ideas on how these go by inspection after a while. If you took this and you worked out f at negative x, you will see 2 times negative x to the 4 minus 2. So don't think, just replace. As you go further, though, you might note that really this is like negative 1x to the 4. So if you expanded that bracket, the negative 1 to the 4 is positive 1. So this is just 2x to the 4 minus 2. And we're back where we started from. So it means f at negative x is equal to f at x, which means that it is even. And you're probably thinking right now, anything with x to the 4, x to the 2, x to the 6 will be even. And you don't want to, that's maybe oversimplifying it a little bit, but that certainly is a tip-off about the nature of the graph. Now we will eventually look at this curve, but next let's do this one. So f at x is equal to negative 2 x to the 3 minus x. A little bit more complicated. It doesn't look like it's going to be even just because of those exponents. Let's see what happens though. F at negative x is equal to negative 2 times negative x to the 3 minus negative x. Keep going. F at negative x is equal to, well, now hold on a second. This is negative 2 times this negative x cubed is negative x cubed. So negative x cubed times negative 2 is positive 2x cubed plus x. So that one does not look very much of anything. However, if you consider that by factoring out a negative 1 from both of those terms, you'll get negative 2x cubed minus x. And in fact, this is negative f at x, because that is the original. That's what the f at x is equal to. So how you can identify the odd function is after you replace x with negative x, you get the same function, but a factor of negative 1 in front of it. So the trick is always to try to factor a negative out of all the terms and see if it takes you right back. So this is going to be odd. Now the next screen will have a couple graphs for us to examine. And you can see by inspection that this is even, the first one. Odd's a little tougher to tell. But in fact, one way to do it is just to take points. Maybe this point right there. Well, it's a little tough to get a point, isn't it? So negative 1. So negative 1, if we work that one out, negative 1 to the 3 is negative 1 is 2 minus, yeah, so this is negative 1, 3. That point, there should also be a 1 comma negative 3 on the curve. And I think you could work your way down and you'll see that it all works like that. So every point xy will have a sister point, negative x, negative y. Let's do a few more. Y is equal to x divided by x squared plus 1. So this is a type of rational function. Don't think too hard. Write this in terms of f. So f at negative x is negative x over negative x squared plus 1. This turns into negative x over x squared plus 1. Now, we can see that it's not even because it's not identical. Question is it odd or neither? So what I will do is factor out a negative 1. And when you factor a negative 1 out, you're really just taking it from the numerator. If you took it out of the numerator and the denominator, you're really taking a positive out. So this will leave you with this. And in fact, this tells me that f at negative x is equal to negative f at x. So therefore, it is odd. Try another one. F at x is equal to 2x cubed plus 3x squared. Remember, anytime, pause me and then see if you want to, and then do it on your own. So 2 times negative x cubed plus 3 times negative x squared. So f at negative x is equal to, well, this is negative 2x cubed, and then plus 3x squared. And what happened here, of course, the negative x squared became positive while the cube did not. You probably can tell what's going on with it, but I'm going to play it safe. I'm going to factor negative out, and I get 2x cubed minus 3x squared in brackets. Well, that's not exactly what we started with. And remember, it has to be negative f at x. So therefore, neither. Close, it looked like it might. Neighbor, neither is what I want. Close, but wasn't quite right. So let's take a look at those two graphs. The first one we did say was odd. That's correct. And yeah, it kind of makes sense. If you take a look at every point there, we'll have a mirror image of it down there. You could also think of this as being, once again, as being a reflection in both axes. So if you kind of drew it, my drawing isn't going to help too much with that. There's the first reflection over the y-axis. I think it would have been actually over either. And then reflected again, and you can see that it lines up, it's back where it started from. And then the second one down here, it is neither. So that's fairly clear by inspection. Do a few more. 6y is equal to x squared plus x. So f at negative x is equal to negative x squared plus negative x. So f at negative x is equal to x squared positive minus x. So now, just to be sure, we factor out a negative, and that would give us, well, factor out a negative from x squared will give us negative x squared plus x. So unfortunately, didn't quite work out. It's going to be neither. That x squared leading was a bit of a concern. And then this one. Number 7 is an odd one because, first off, the way it's written, it's not a function. So that's what's going to bother people right away. But when we work this one out, we get negative x to the 4 over 4 plus y squared is equal to 1. So this is x to the 4 over 4 plus y squared is equal to 1. I'm going to note that this is not a function, and we can tell it's not a function because it's got a y squared in the term, and some of you might remember what the shape is for Math 30 Pure if you've taken that. However, by the work I've done, you'd say, well, hey, this one is even. But let's take a look at the graphs. First off, the one here we described as being neither. This one here, well, it clearly is even, but you know what's interesting as well is that if you take some of these other points, it's also going to be more than just even. It is symmetric over the y, but this is also symmetric over the x-axis. This, in fact, is an example of a question that is you would probably not refer to in terms of being even or odd. The way it is given now, it is symmetric about the y-axis, x-axis, say the word and the x-axis. So, in fact, you could, if you describe this one as being even, you'd be correct mathematically. You'd also be correct to say that this is an odd function as well, too. Each of those points that you have will have a mirror image, like this one over there is going to reflect down perfectly over there. The key idea is that it's not a function. So the method we use to check for symmetries is totally reliable with functions. If you get a non-function like this, such as a circle and ellipse, then you either have to do a little more work visually to compare it or else reject the question because it's not a function. That sort of question should only come up in function-type problems. So that's just more of a curiosity than anything else. Now the very last one, f at x is equal to x to the 1/5. Here as well I'm going to take a look at the graph of it. This is the 5th root of x. And if you were to replace it with negative x, 5th root of negative x, the way to think of this is that this is the 5th root of negative 1x. And if you took the 5th root of negative 1, it is negative 1. So this is, in fact, equal to this. Now this tells me that this graph is odd because it is negative f at x. And then this graph will verify that. It looks like everything is pretty much perfectly symmetric about the origin like that. Every point will have an equal sister point down below. So that's it for this lesson. The next one we'll do some more work with graphing and split functions and continuity before we then get into the limits and do any review on this. So thank you for your time.